In this video, we're going to talk about the wonderful world of Proton NMR. Okay, so you've already done carbon NMR, but this Proton NMR is a little bit more of a puzzle and therefore a lot of fun as long as you put the effort in and time to master it. Okay, so we're going to do this video which goes through some clear examples of how to do it with different types of molecules, and then there's going to be many videos which give you an example to try, which I'd like you to have a go at, and then I explain how to do it. And each one of those videos will teach you a lesson about Proton NMR. This is the basic get started video. And therefore we're going to talk about the hydrogen environments and the n+1 rule. So uses of Proton NMR. We find out about the nuclei of atoms like we do in carbon NMR, but this time it's high resolution and therefore we get peak splitting, which I'll explain later. We find, as in carbon NMR, the number of nuclei and the environment they are in. And it is going to be in your exams. No question. You cannot not learn this. This is one of the most important areas to learn in organic chemistry. It will come up normally as an LOR question in the last few years' worth of chemistry exams, which means you have to predict a structure to get anywhere near full mark. So just to remind you, the reference used in Proton NMR is tetramethylsilane, and that is used because it has the chemical shift of a 0, which is well away from everything else, just like it is in carbon NMR. It also uses deuterated chloroform as a solvent, because the deuterated chloroform doesn't create any peaks. Now the tetramethylsilane is used as a reference because of this 0, and here is your tetramethylsilane with all of these hydrogens in the same environment, because planar symmetry in any direction, they're all in the same environment, and therefore they get this lovely strong peak. And that's that orange line here, and that gets set to 0, but in the machine it gets rid of that peak so you can't see it. And that's why they use tetramethylsilane. We're now going to talk about hydrogen environments just like we have done with carbon environments. Now, with ethanoic acid, we have two sources of hydrogen. We've got the hydrogen here on the carbon, and we don't talk about individual hydrogens, it's just hydrogens on a carbon as a group. And we've got this hydrogen on the OH there. So we have two carbon environments. Now, it's really important though that you know the exam tips before we carry on. So the exam tips are, with NMR, if you get a peak and it is close to an electronegative element, like this H to here, and like these H's to this C double bond O, because they're both close to electronegative elements, they move something called downfield. They'll get a higher ppm. Okay, but we'll talk about those in the examples. Now, most important thing though is use the data sheet. Okay, so have the data sheet in front of you right now. If you don't have it, pause the video, get the data sheet. Now, as I said, there are two carbon environments. Now, if you look at your data sheet, you can see an OH comes out between 0.8 and 12, and this, because it's connected to the C double bond O, you see a C double bond O, CH, so there's your C double bond O and then CH. Okay, and that means that will come out between 2 to 3, and this will come out between 0.8 and 12. Now, what peaks are you actually going to see? So before I go into more detail about ethanoic acid, I want to show you what type of peaks you'll see with our two hydrogen environments. Now, this is to do with something called the peak splitting or n+1 rule. N is equal to the number of hydrogens on the adjacent carbons. And that's carbons only. Okay, and we'll talk about that when we go back to ethanoic acid, but carbons only. So you're looking in your molecule of what carbons are around your hydrogens, not the carbon that the hydrogen is bonded to, the carbons around that, and how many hydrogens are on those surrounding carbons. So if you find that it's 0, 0 plus 1, because n+1 rule, is equal to 1, which means you'll see one peak. And we call that a singlet. If you find there was one hydrogen on the adjacent carbons, then it's 1 plus 1 equals 2, and therefore we'll see two peaks. And that's called a doublet. If we have two hydrogens on the adjacent carbons, 2 plus 1 equals 3, and therefore you get a triplet, 3 peaks. And then n equals 3, 3 plus 1 equals 4 is a quartet. Now these are the main ones you're going to have to know, okay? So you're going to have to know these four. You can go further, so, and you can keep going. N equals 4, for example, 4 plus 1 equals 5, and you'll get this kind of pentet or quintet. Now that can also be called a multiplet when you get to that level, okay, because it's not really assessed in terms of splitting to that level, but it's good to understand because it helps you understand what kind of molecule you've got in front of you. But this is what we call peak splitting, and that's what you're going to see on the NMR. So you're going to see it in a certain ppm, a certain chemical shift, which is what we've already done, and you're also going to see peaks coming that look just like this. So let's apply this to ethanoic acid. Move this down and put our ethanoic acid in. We think we've got two environments, here and here, okay, an OH and a CH3, and those two environments we think are going to come out between those two places. We now need to decide what kind of peak splitting we're going to get. Now notice as well, if I go up here, I've also put the word coupling in. So the word coupling is sometimes mentioned. I know when I was doing my degree we used the word coupling, not peak splitting. Okay, so if you see coupling, it just means peak splitting. Now, let's see how these peaks are going to split. So first of all, this peak here, let's look at the adjacent carbon. There are no hydrogens on the adjacent carbon, so it's going to follow n equals 0, 0 plus 1 equals 1, singlet. We then look at this one. Now, this is really important. I'm going to highlight this here. Okay, carbons only, on the adjacent carbons only. Now, as soon as that hydrogen reaches oxygen or nitrogen, for that matter, okay, there is no peak splitting. It's like a blocker to any kind of peak splitting. Okay, that means it acts as if there is no hydrogens on the adjacent carbon at all. So it goes n equals 0, 0 plus 1 equals 1. And that's why you get that singlet. So we've got two singlets and we've got our chemical shifts. We think we know roughly what they're going to look like in terms of taking it off the data sheet, and that would be fine in the exam. Now let's put it into a table. So once it's in the table, we can also put in something called a relative peak area. So the relative peak area is in the top corner here, and that tells you how many hydrogens give rise to the peak. So how many hydrogens are there? So if you look here, there is 1, 2, 3 hydrogens, so I'm going to put 3 there. There is 1 hydrogen there, so I'm going to put 1 there. And I've got a full table. Now, sometimes in some exams, one level can equal a mark. Okay, so if you just do the table, you can get the mark. And you can just copy the areas off the data sheet if you need to. Okay, but we're going to do a bit more detail later on in the next slide. So, let's take this and then look at the NMR itself. So here's your NMR and here's your table. So, first of all, we've got our actual ppms here, okay? And in the actual exam, you would have to find the exact ppm, not just give the ranges. You would have to go down here and give the exact ppm, but we'll do those in further examples. And also in the actual exam, you'd have to look at the type of proton. So that's good, but it doesn't really help you make the structure. So I would encourage you to do it more like this. Where you think it is, it's got a relative peak area of 3, so that means this must be 3 hydrogens, which means the actual type of proton will be CH3, C double bond O. Okay, and that would be your NMR table, apart from these more precise chemical shifts for ethanoic acid. The next example will be propane, and we are using propane just because it is an example of symmetry. So if you look down this molecule, you can see it's planar symmetry, which means that we don't actually have 3 hydrogen environments. These 3 hydrogens here are in the same environment as these 3 hydrogens here because you can draw a planar symmetry down the middle. So therefore, same environment. Now CH2 is in a different environment because if you look, it has a CH3 next to it, okay, and it has a CH3 next to it, okay. So 2 environments for this molecule, and we think they'll come out between here and here because we've looked at our data sheet, okay, because they're just RCHs. Now, if that is the case, we've got that symmetry, we can now turn it into a table. So here we have our table, the chemical shift, type of proton, and peak splitting. So our chemical shift, we think, will come out somewhere between there, and our type of proton will be RCH. Now let's look at our peak splitting. Now, if you look at this peak, remember this is the same as this one here. So that means that there's 2 hydrogens on the adjacent carbon. So 2, and 2 plus 1 equals 3, which means we're going to see a triplet. And the same on the other side. But we're going to see a triplet, which is caused by 1, 2, 3, 4, 5, 6 hydrogens, or 6 protons. And then the next one, if you look, these hydrogens, the adjacent carbons have 6 protons on, so n equals 6. 6 plus 1 equals 7, so that is a heptet. Again, you can call that a multiplet if you want. So we think we're going to get 1 triplet, but the 2 signals overlapping because they're in the same environment, okay, and 1 heptet. And let's put those into the table. So remember, they're the same environment and therefore straight over the top of each other. Now, relative peak area, as we said, this is caused by 2 protons, but these signals are caused by 6. Okay, now, if you look at that, this is where it comes into relative peak area. Now, relative peak area is a relative term, therefore it's to the lowest ratio. Okay, so basically instead of 6 to 2, you would see 3 to 1. Because you would see 3 to 1, you need to be aware of that when you're looking at the examples. But we're going to go through several examples that use this, so don't worry about it for now. Now, if we can take this table and then we can turn it into an NMR. So here we have our NMR, and there's a very, very small peak down here because it's only 1, which you can barely see, okay, but we've highlighted it and made it larger there, and there's our heptet and our triplet. And we've got the ratio of 3 to 1. Remember, it's 3 to 1, even though it was 6 to 2, because it's the simplest ratio. Now, if we're doing this properly, and we started with the NMR first, we would look at the chemical shifts, get our ruler out, and find out exactly where the chemical shifts are. So I can tell you they're at 0.8 and 1.4. And also, if we're doing it properly, we would be more detailed about the type of proton. So the type of proton here is CH3 and CH2. So that would be our finalised table. Now, we've gone through 2 examples that use symmetry and just use electronegativity to give you an idea of the peak splitting and what you'd see. Okay, and hopefully you've now got an inkling of how to do, at the very least, ethanoic acid and propane.